Hello friends, I am Ashutosh Kumar and today we'll progress on our next tutorial of theory of computation. Okay, in previous tutorial I gave you one problem, so let us see how we draw that. Okay, the problem was to draw a model for this language, and the language was L equal to x belongs to okay. So this was the previous problem. Okay, we have to draw the machine, the model for this problem. Okay, and for now just consider that whatever we are drawing the model, it is DFA. It is DFA. We are currently dealing with deterministic finite automata. Okay, we are currently dealing with deterministic finite automata. Okay, before I solve this, let me give you some idea. So we have, we have this type of thing, FSA, that is finite state automata. Okay, so finite state automata can be with output, okay, and can be without output. Okay, so this finite state automata can be with output or without output. Now under this we have NFA, we have DFA and NFA. Okay, we have some more, we will see, but just consider that we are dealing with without output type of model, and under that we are dealing with DFA. Okay, why without output? See, in the example done in the previous lecture, we only checked that whether the language is accepted by that model or not. So here in DFA we are checking that, and we call it deterministic. Why? Because see, when we have a state, we have a state, and when we have some input, okay, when we have some input string, then we know that either we have to go to this state or remain in this state or go to some other state. Okay, this was the case of deterministic that we are dealing with. In case of non-deterministic, when we have a state, giving input, suppose I am giving 1, okay, it can either go to this one or either go to another state, so it is not fixed. Okay, so we will deal with non-deterministic automata, but for now we are discussing DFA. Okay, we'll see DFA only. Now let us first solve this problem. See, in this problem we have to decide that the string that will be accepted will have even number of zeros and even number of ones. Okay, so what we can think of that, see, states, I am drawing those states. What states we can have? Okay, we can have even 0 and even 1. Good. We can have even 0 and odd 1. We can have odd 0 and even 1. We can have odd 0 and odd 1. Okay, so these are the 4 possible states, okay, that we think of, and we will switch our state, we will change our state of mind among these only. Okay, we will be flipping from this to this, or any combination. Okay, so we got that these are the 4 possible states. So we are see how we are formally modeling modeling. We are not modeling, we will create a model, and that is what we formally call it DFA. Here we are forming a deterministic finite automata. Okay, let us see how we'll do it. Now let us name, okay, we'll name even and even. Okay, we'll name this as state, say for example Q1. Okay, we'll name this state as Q2, this state as Q3, and this state as Q4. Okay, I have named it that these are my 4 states. Now let me draw those states. At first I draw this Q1 state. Okay, this is my Q1 state. this state tells you that you have even 0 and even 1. And then see, when I have drawn this state, when suppose we have a string like this 0 0 1 1 0 0 1 1. Okay, so we start from just empty. We have seen no string, here. That is, we haven't seen any 0 or we haven't seen any 1. Means we have seen 0 number of zeros and 0 number of ones, and 0 is an even number. So we can say that our initial state is like this. We have seen 0 number of 0 and 0 number of 1, and that comes out to be that we have seen even 0 and even 1. Okay, now this is the state, initial state. See what happens if we encounter a 0. I have reached at q1 state. We have our state of mind is at q1. Now suppose we encounter a 0. Okay, we encounter a 0 here. Okay, so what we'll have, we have seen 1 0, we have seen 1 0 and 0 1. Okay, we have seen 1 0, that means 1 is odd. So see, we have seen 1 0, so we have seen odd number of 0, and let me write it like this way. This is your q3. Okay, so when I see a 0, I go here. Why I go here? Because seeing a 0 makes your number of zeros odd and number of 1 is even only because you haven't encountered any 1. So q3 is even 1 and odd 0. Very good. Now what if you see 1 here? If you encounter a 1, suppose if we would have encountered a 1 at this state, where would we have gone? So we would have gone odd number of 1 and even number of 0, odd 1 and even 0. So let me draw q2 here. Okay, I have seen an 1. I'll go here. Okay, good. So I have completed this state, that for 0 what will be the transition, for 1 what will be the transition. Now let us see what happens at q2. See, q2 is having even 0 and odd 1. Now if we encounter a 0, here, what will be this? This will be odd 1. Okay, odd 0. So we have odd 0 and odd 1 will go to q4. See, again q2 is having even 0, and when we encounter a 0, number of 0 will be odd, so we'll go to odd 0 and odd 1. Okay, so we have seen a 0, we went there. Now what if q2 sees a 1? At this state you scan a 1. If you scan a 1, again go to q2, you are scanning 1, so you are making number of ones even, so you go to even 0 and even 1. So what will be the transition here? We'll go to here, isn't it? Again, so we have, sorry, this is 1. Okay, so you have encountered a 1, so you have made 1 to even, you went here. Now see, I have completed q2 for 0 and 1. Let us complete q4 for 0 1. Now q4, when we are at q4, if we encounter a 0, so we are making number of zeros even, so we'll go to even 0 and odd 1. So even 0 and odd 1 is q2. Very good, we are seeing a 0. Okay, now if we encounter a 1, so if we encounter a 1 at q4, what will happen? Odd 0 and even 1. So odd 0 and even 1, q3. I will go to q3 by seeing a 1. So I have completed 0 1 for q4. Now let us see what happens at q3. Now q3, if I encounter a 0, we will have even 0 and even 1, and even 0 and even 1 is q1. So after seeing a 0, I will go back here. If I see a 1 here at q3, if I see a 1, then what will happen? Odd 0 and I have seen a 1, so this even will be odd now. So odd 0 and odd 1, so odd 0 and odd 1 is q4. So I go here. See, this is our state transition, okay? The state transition diagram. Now, see, we have to accept those which have even number of zeros and even number of 1. So state Q1 is having even 0 and even state, so even 0 and even 1. So let us make this state a final one. Okay, so this way we have completed the transition diagram and we have drawn a model. So this model we can write as LM. When we write this model as LM and L is defined here, this means this model, this machine M is accepting the language L. Okay, so see, if I put a 0 0 1 1 0 here, let us check whether this string is accepted or not. By saying accepted or not, we mean that at the end of scanning we have to reach at Q1. Okay, so we'll check this one. So we have this string 0 0 1 1 1. So before anything, we haven't seen anything, so we are at a state Q1, aren't we? See, we haven't seen any symbol, we haven't scanned any character, then we have seen no 0 and no 1. So at initial state we are at Q1. Now I have seen a 0, okay, I have seen a 0. No, now I am at Q1 and I have Q1 and I have seen a 0, okay. From Q1 I have seen a 0, I will go to Q3. So my state is Q3 now, okay. Now I am at Q3 and I will now see this 0. Very good. After seeing this 0, so from Q3 to 0, Q3 to 0, see, again I am going back to Q1, so I went back to Q1. Now Q1, these two are seen, I have to see 1. From Q1 to 1, see, from Q1 to 1 will go to Q2, so Q1 to 1, Q1 to 1 will go to Q2. Now we have seen this one also, again a 1 will come. So Q2 to 1, from Q2 to 1 we have seen a 1. So where we will go? From Q2 to 1, again we are going to Q1. I have seen this one, again I have encountered a 0. So see, from Q1 to 0, Q1 to 0, Q1 to 0, I am going to Q3. Again this one is done. Now we have a 0, again we have a 0, so from Q3 to 0, Q3 to 0, I will go to Q1. This 0 is done. Now from Q1 to 1, Q1 to 1, I will go to Q2. This one is done. Now from Q2 to 1, Q2 to 1, I am at Q1. See, finally we reach at Q1 and this Q1 is your final state, isn't it? So see, scanning these strings, I reach at Q1 through this model. And one more way of doing this is using this delta hat. I told you the notion of this. How we do? We put a state Qi, comma string x, okay, and simply inductively you can follow and reach through this. So this way you can check. Now let us check whether 0 0 1, what gives at 0 0 1, okay. So initially we haven't scanned anything, so we are at Q1. Okay, we are at Q1. Now we have seen a 0. So Q1 to 0, Q1 to 0 takes you to Q3. Now Q3 to 0, Q3 to 0, Q3 to 0, it takes to Q1. Good. Now Q1 at 1, Q1 at 1 takes you to Q2. See? So we have reached Q2 and Q2 is a non-final state. So we say 0 0 1 is not accepted by L or this model, okay. So 0 0 1 is not accepted and this was accepted. So this was the the example that we had to solve. Okay, now let us proceed. Okay guys, now let me give you notion of acceptance. Okay, many people have confusion about this, so let me write. See, the previous example that we did was like L x belonging to 0 1 star, x has even zeros and even ones. Okay, so this was our language. Now suppose my question is, I tell you we have a language L equals to 0 0 1 1 0 0. Okay, this was the language and we draw a model. We draw a model M. We actually did draw it. Okay, we actually did draw some minutes back. So the model was M. Okay, let us name that model as M. Now tell me whether this language, for convenience, let me, whether L1 is accepted by M or not. So my question is whether L1 is accepted by M or not, and this M is the previous state transition model that I draw. Okay, now okay, then you will say yes, this is having even number of zeros. So yes, when we go through that transition diagram, we'll reach to a final state. Again, this element is also making you reach to the final state. So people will argue yes, L1 is accepted by M. Okay, but L1 is not accepted by M. Now it may sound weird, but you know why? See, what this language was, this language was having x belonging to 0 1, and x has even number of zeros and even number of ones. So x contains all those strings, or all those strings that have even number of zeros and even number of ones, and we draw a model for this language that was M. Okay, so any even number of zero or even number of odd was accepted by M. Now when I say this thing, so L1 is having 0 0 1 1 0 0. So see, basically when we say that L1 is actually a subset of L, isn't it? So L1, suppose this is L, so L1 is somewhat like this, isn't it? And what is M? M is much more, M is accepting this L. Okay, so see what I mean to say now. In this model, if I say L1 is accepted by M, if I argue that L1 is accepted by M, then let me write a string like this one. So this will also be accepted by M, isn't it? For instance, consider this model. Now just do not go to this. Okay, we have a model that we came up with this one. Okay, now we have a model. Now this is the language that we are focusing. Okay, and I am saying that this L1 is not accepted by M. So my point is, suppose this L1 is accepted by M. Now I may give you this string and say, okay, this is also accepted by M, isn't it? But this is not in this language, isn't it? So whenever we say that a machine is accepting some language, it must accept that valid string and also reject non-valid string. See, this is not belonging to L1, but still this will be accepted by M, and this should not happen. Got my point? Whenever I say that L is accepted by M, this means this language is accepted by M, then every valid strings belonging to L should be accepted by M, and all other strings should be rejected. All other strings should be rejected. Means suppose we have all the strings that are belonging in this L should be accepted by M, and all rest of the strings should be rejected. Now here all the strings belonging to L1 are accepted to M, but see all other strings, this is one string, so this is nowhere you are going to reject it, this will also get accepted. So when I say about acceptance, it is not only about acceptance, it is all about acceptance plus rejection. Okay, so, and this was one point. One more point you can justifies this. If I say this L1, isn't it this L1 is a subset of L? aren't we? So when we talk about that a language is accepted by M, it must be a complete language. Okay, by complete I mean that all the strings belonging to this set will be accepted, and rest one will not be accepted or must be rejected. Okay, so by this I mean this. So what is the L1? L1 is a small part of L, but M is what? M is something bigger. It is going to accept more number of strings, and that is contained in this L. So L is giving you that complete number of strings that will be accepted, and all other strings that are not in L will always be rejected by this M. So we say that this L is accepted by M, and this L1 will not be accepted by this M. And we can separately draw a model for this L1. We can separately draw a model for this L1, and that will be different from this M. So this is M, and we separately draw a model for M1, then okay, this L1 will be accepted by M1. Then we have to separately draw a model. Got my point? So basically, see, this is finite, and one more important point you should notice is this is finite. You are having a finite number of string. I will come to this when I go to regular language about finite and infinite, and this was infinite, isn't it? Why? We can have infinitely many strings. Okay, but here I have restricted. I have only two strings in this language. Okay, so we'll have an infinite one and we'll have finite one. We'll see the impact of infinite and finite when we come to regular language or regular expressions. Okay? So this you must be clear about. And one more important point is that suppose I have drawn as automata like this. Okay, so any input you give, suppose I am in 0 1. So again you will say that this L1 is accepted by, see, these strings are obviously accepted, but this language is not accepted. Why? Because anything you give, you are always going to be in final state. See, I have made this a final state. So this is basically sigma star. This language is equal to sigma star. So this sigma star will be accepted. Now our language is sigma star, and when I say language L1, which is a strict subset of L, isn't it? A strict subset of L. By strict I mean that some of the elements of L are not in L1. Then this L1 is not accepted. So when we say that a language is accepted, then we do not mean superset or subset. We mean that language, complete language. Okay. So this was notion of acceptance. Keep in mind, many people miss at this point of time, and you get objective questions, tricky questions related to this one. Okay, now let us move on. Okay guys, so you saw the notion of acceptance. Okay, and now we'll discuss about regular language. So let me write one point about the notion of acceptance is that, see, L x belongs, sigma star, then delta hat what I've written is that this is actually about the acceptance. Okay, isn't it? So x belonging to sigma star, and if a string x takes you from initial state to a final state, this f, then it is accepted. And we saw that for acceptance we do not talk about this subset or the superset, but about that language, and every element of that language should be accepted and others must be rejected. Okay, now let let us talk about regular language. Okay, so we can write, let me write the definition first. See, I have termed this language L regular. A language is called regular if we can draw a DFA for it. Okay, so we were drawing DFAs. Okay, now suppose this is a language L, and we draw even zeros. X has even zeros and even ones. So we could draw a DFA, okay? We draw a DFA, and that DFA, that machine M was what? Characterized by 5 tuple Q, sigma, delta, initial state and final state. So if we can draw a DFA for language, then that language is regular, okay? Now, I told you about finite language and infinite language. In finite language, we have a finite amount of elements, okay, and in infinite the elements are infinite. Suppose I say language L equals to AB, AA, BB and BA, okay, defined over alphabet AB, okay, then this language is finite, okay, and every finite language is regular, okay. So we can draw uh, DFA for finite language, okay. Because we have, you know, finite, these strings are finite, so we can draw a finite amount of state, and we can just conclude that finite languages are regular. Now this was an infinite language and it was regular, it was also regular. So whenever we are able to draw DFA of a language, it is regular. Now it is another question how we will, you know that whether we can draw a DFA or not. That will analyze. We have certain theorems. We'll see pumping lemma in due course of video sessions. But for now, we will just take a language and we'll draw a DFA model for it, and we'll say that the language is regular. Just we have to get the notion of regular language, and in future course of video sections, we will see how we'll prove whether a language is regular or not. Okay. So now let us consider an example. I write a language L x belonging to sigma star, that is 0 1, and x has 0 1 as substring. Okay, so we want to draw this one, and we have to draw a model. We want to draw the model, in fact. So can we conclude whether this language is regular or not? So let us try to draw a DFA. Okay, I'm trying to draw a DFA. So let me name a state as Q1. This is the initial state. So till when we haven't scanned any character or any input, so we are at this state. We haven't scanned anything. Now we have scanned, suppose A0 or 1. Let me first draw it, then I'll explain you. See, and I am making this one as a final state. Now see, okay, I have to get a 0 1, okay, in a string I have to get a 0 1. So when I am at here, this state, if I get an input as 1, okay, then we say no, our target was to get a 0, because we are searching this 0 1. That if we face a 0, then we are, we have some positive attitude that yes, we can get a 1. Now we are toward our goal. But here if we get a 1, so we have to first get a 0, then we'll come to this goal. So we got a 1, then we'll say no, I will remain in this state only. There is no significant achievement to our goal. Now if we get a 0, we say yes, we can proceed. So what we did, we made a new state, and at 0, scanning 0, we proceed to Q2, from Q1 to Q2. Now this state, if this state is getting a 1, if I get a 1, then say yes, we got a 0. Now at this state we got a 1, so 0 1 is a substring, so I get into the final state, and that's why I made Q3 as a final state. Now what about 1? What about 0 at Q2? See, I have done 1 and 0 for Q1. I have done only 1 for Q2. So what about 0? So if I reach after, suppose there were certain string characters, and then I scanned a 0 and I reached to Q2. Now I got a 1, so I concluded that yeah, I got to final state Q3. Now what if there was another 0? Again we would remain at this state only in hope of getting a 1. So we are here, and now if we get a 1, it is okay, I am here. Now we have when we are at Q3, we have scanned 0, 1, okay. So we concluded that yes, 0, 1 is present in that string. So whatever may be the input further, we don't care. We'll remain here. Okay. So let us check how we'll check it. Suppose I am telling you that check this one. Is this belonging to, is this accepted by this language or not? Okay. So for that, see, we are at Q1. We haven't scanned anything. Then we got a 1. We got a 1. We got a 1. After getting 1, we will be at Q1 only. Then we got a 0. So at Q1, we got a 0. So we'll go to Q2. Let me write 1, 0, 0 and 0. Okay. So Q2. When Q2, at Q2 we got a 0. So again we will remain at Q2. And again at Q2 we got a 0. Again we will remain at Q2. Isn't it? So see, Q2 is a non-final state, so this is not accepted. Now suppose this is string 1, 0, 0, 0 and 1. So let us draw this type of arrangement for this. Now we have got, we are at Q1 and we scanned a 1, 0, 0, 0 and 1. So Q1 at 1, Q1 at 1 will remain at Q1. Q1 at 0, Q1 at 0 will go to Q2. Q2 at 0, Q2 at 0 will be at Q2 only. Again Q2 at 0 will be at Q2 only, and again Q2 at 1 will go to Q3. So we reached a final state, isn't it? So this is accepted. Now this was about, saying that this language is regular. Why? Because we are able to draw a DFA. Okay. Let me point out you one important thing. See, I have a machine M that is characterized by like Q sigma delta y. Yeah. Suppose I write like this. From some state, say from Q1 to X1 and then Y equal to delta hat Q1 X2 to Y. Okay. See, when I write A, B or C, okay, this will mean that we are talking about a single character in a string, like, okay, like 0, 1, 0. So this single 0 can be represented by A, B and C. And when I talk about X, Y, okay, that means I am talking about the whole string. So this 0, 1, 0 can be represented by X or Y, and this single 0 will be represented by A or B or C. So this is only convention. So suppose we have a model M like this, and we are at a state Q1, okay, we are at a state Q1, and after scanning this X1, okay, after scanning a string, okay, we reach to a final state, we reach to a state, say P, okay, this X1, and also after scanning X2 we again reach to P, okay, starting from Q1, this is a state starting from Q1. When we scan X1 and we are at a state Q1, say we reach at P, and again if we scan X2, a string X2, and we are at Q1, this is Q1, then we again reach a P. So yes, it is good. Now at state P, when we scan Y, again we scan Y, so obviously we'll get a same state. Say the state is Q, for example, Q, okay. So yes, both these are equal, but this finite state automata, when we talk about, it will not be able to tell you that which string took me to P, whether X1 or whether X2. It cannot remember in its finite head. So this is the point that I want you to make, is that when we talk about finite state automata, it cannot remember things like this, or it cannot do any arithmetic division or anything. Okay, we'll see, we'll draw a DFA, and in that DFA we'll calculate about, like for example, we'll have a language L and X belonging to some sigma, and we'll say that X is 2 mod 3, something like that. Okay, we'll calculate DFA in example sections. Then when we'll draw the DFA of this arrangement, that doesn't mean that our automata or that our model can do this type of calculation. Well, we'll see how we'll work out this. So I want you to make a point is that it cannot remember this type of things. It is not able to differentiate which string, whether x1 or x2 took me to a state. Okay, so just keep these things in mind. Only the thing that this model will say, okay, if we scan x1 I am at p, again if I scan x2 I am at p, but I don't know which x1 or either x2 took me to p. Okay, now let us draw a DFA of a finite language. We did draw the DFA of infinite languages. That was now let us see. Suppose L is a language like A, AB, BA, and BB. Okay, this is obviously defined over sigma equals to AB. Already draw the DFA. See, simple. Will we at a initial state? Say the state is Q1. Okay, so let me mark this as initial state. Okay, then what? We have to reach a final state, and then I draw Q2 and a Q3. Okay. So if I scan A, we reach to a state, and again if I get a A, it should be accepted. So again when I get a A, it is accepted. What about this AB? So this is A. Then at Q2, if I get a B, then also it must be accepted. So I write here B, isn't it? And what about BA? So if we are at Q1, we get a B and A. So here we write a B also. So we scanned B, we got at Q2, and again from Q2 we scanned A and we got at the final state Q3. Similarly, B and B can take you to Q3. Now what if a See, what I am drawing here is that suppose at Q3 we get some more elements. Suppose we scanned like this A, B. Then what should be the state? So at A up to this we are here. And what if we get a B? Whatever we get after these two characters, we must be not in a final state. So this is a trap state. Okay, this is a trap state. Just keep in mind. So we got a or we got a B from this alphabet set, and then we will be at a Q4. Say this is a trap state, and from here we are never going back. Okay, and again at Q4 you get anything A or B, you will get here only. So this was a trap state. So this was a finite language, isn't it? And I told you that every finite language is regular. It is regular. Okay, so friends, we got the notion of acceptance. We saw that when a language will be accepted by a DFA, and we differentiated that when we say that a language is accepted by DFA, there must be some string that do not belong to that language, and that must be rejected by the DFA also. So we got the notion of acceptance, and we also got notion of regular language. So basically what a regular language is, a regular language is that language for which we can draw a DFA, and we got notion of trap state, isn't it, at the final example, or we are doing that. And we also saw that every finite language is regular. Okay, so this was the key points that we studied thoroughly, and also I told you that we should keep in mind that when we say language is accepted by mod machine or DFA M, it doesn't mean that any language L1 which is a subset of L, so that this L1 will also be accepted by this M. So when I say that this is a machine, then there must be a unique language. Okay, there must be a unique language that will be accepted by this M. Okay, and that even odd example we saw that L was the language which defined over a string alphabet 0 1, and it contain even number of zeros and even number of words, and we draw a DFA, and when I say that this is a language C00 1100, so this is not accepted by that model. Why? Because when we talk about this L, basically this is a subset of L, and obviously see these two will be accepted, but this will not be rejected. Okay, so every element belonging to the language should be accepted, and the elements not belonging to L should be rejected. Then only we can say that L is accepted by M. And obviously when we talk about the acceptance of a language for a machine, then that machine should have a unique language. Okay, that's all today for guys. In the next lecture we'll continue.